So, okay, let's get started. So, in the previous class, we briefly learned about how the functions are called by main function or parent functions. So, actually, I explained which operations are required for handling procedure code. So, actually, in a textbook, it is called the procedure. Okay. So, but we can code that is also functions. Okay. So, okay, actually, we frequently use functions in our high-level language code, actually in C or Java. Also, we can use function in the Python, but the Python is the interpreter language. So actually, the function code of Python is a little bit different from the function code of the C or Java. So a compiled language. Okay. So in order to approach function code, so RISC-V provides the jump instruction. Actually, RISC-V provides the two types of jump instruction, like jump and link, and then jump and link register. Okay. So I explained that actually in the previous classes we also learned about the conditional branches. Okay? So conditional branches check the condition of the branch instruction, and if the condition is true, then this branch instruction performs jump to the target of the branch. But jump is different because you cannot find any condition in the jump instructions, right? So jump means that it's the unconditional branch actually. So which means jump, if the jump is executed, then the program actually processor change the PC to the target of the jump instruction. Okay. So and then if we cannot find any condition, actually we can find some destination register in the jump JAL. Also we can find the source register, but the properties of these registers are different from the source registers of conditional branch instruction, right? The JAL is executed, the PC is changed to the target of the jump instruction, the JAL, and then in the RD, in the destination register, the next PC. So actually, I also explained that the instructions of program is pointed by program counter, right? So which means that this instruction, jump instruction itself, has also its own PC. And then what is the next PC? It's the PC plus 4. It is because the size of a single RISC-V instruction is 4 bytes. And then I also explained that the most processors use the byte address. So which means the 1 byte. So address 1 is assigned to the 1 byte space. So it is because the size of a single RISC-V instruction is 4 bytes. The next PC becomes the PC plus 4. Okay. So PC plus 4 is stored in the destination register. It is because when the execution of a function completes, then we need to return to the parent function or main function, right? And then in order to return to the parent function, then you need to know the return address, right? Because we need to return to some position of the main function, right? So that's why we need to store the next PC is x1. Okay, and then so I also explained that we need to return to the the parent function or main function. So which means that using this stored return address, then we need to return to the parent function. So we can use the JALR. So actually, only this part is different compared to the JAL, right? In the JAL, we use the target. The target defined by label is we use this label, the program count of this label at the target of the jump instruction. But if we use the JALR, so this is the source register. So a processor read data from the source register, and then the value of the source register is added with the offset, which is the immediate value, right? So it's immediate value. And then the PC is updated by this value, okay? So if we use the 0 and then, the x1 is the same, then actually the PC becomes the x1 stored by previous JAL, right? Understand? And then so JALR has the destination register, but in this example we use the x0, and then I explained that x0 is the 0 register, so which has already 0 value, so it is not updated. Okay, so actually this is nothing. Okay, so and then that's the example of function code, and then how this function code is processed in the computer system. So this is the example code. As you can see, this is the function name, RISC example. Oh, so I need to explain. So actually there are two kinds of functions, right? So some function, like the main function of the C program, this is also function. So this main function can call other function like foo, and then inside of this function, then this function can call also the other function foo. So, but this function can be the last function called by main function. So which means that this is the last function. So which means in this function, there is no other function calls, and then we can just find return at the last line of this function. So then this kind of function is called the leap function. So it's a leap procedure. So in a tree, so this is a tree, and then you can find some branches here, but leap is the last part of the tree, right? So we can find root here, and then we can find some trunk here. We can find many branches from trunk. So, but the last part of the tree is the leaf. That's why this function does not call any other function. So this type of function is called leaf procedure, which means the last function. Okay. Let's see how this leap procedure works in a computer system. So we can find function name here. Also in a C code, we can find the data type of the return value. So function will return some result to the parent function. So we can find 4 arguments here. These are input data of a function. Okay, and then inside of a function, the new variable is declared, and then so this statement is executed, and then when the function completes its operation, its function returns result stored in F. And then this is some assumptions, and then we assume that input arguments like G, H, I, J are stored in registers from X10 to X13, and then inside of this function, then function also needs to execute instructions, right? So if this function is compiled, this function also will generate RISC-V instructions, right? RISC-V assembly instructions. So inside of this function, new variable is declared, so which means that we also need to store the value of f in the register. So f is in x10. And then also, in order to execute the arithmetic instructions, so we know that in order to perform this statement, we require add instruction and then solve instruction, right? So, and then, we add instruction, it looks like add x1, x2, x3. So which means that we need to store the temporary values to the some registers, okay? These instructions are also executed in a processor. So in this example, so these temporary values are stored in the x5 and x6. Then what is the problem? So let us assume that this is, so we have a main function, and the inside the main function, this lip example is lip example is code. And then this is the assumption of this lip example. Okay, and what is the problem? The problem is that, inside of the lip example, then this lip example will registers x20 and x5, x6, right? And what's the problem? This function does not know what? Maybe in the parent function, x5, x6, and x20 are already occupied by other instructions, right? So when this function is executed, this function needs to use x20, x5, x6. But before this function is called, a parent function or main function may use these registers already. Then what will happen? If a function updates these values, these registers, then the values in these registers will be lost. Okay, that is the problem. So what should we do? In order to save the values in these registers, what should we do? We need to store the values in these registers in temporary storage, right? So x20 has some values like A, x5 has some values B, x6 has some values C. So when the function is called like the leave function, then x5, x6, x20 will be overwritten. Okay. Then we should the values, the old original values in these x20, x5, x should be stored in the temporary storage, right? And then if the function call is completed, then we can reload the stored value to the x20, x5, x6. Do you understand? Because the registers are, the number of registers is limited, so we cannot increase the number of registers. So I also said that the registers are very precious resources in a processor. Okay, so actually with the high probability, these registers may have some values, okay, old values. So and then when a compiler compiles this function, then compiler try to occupy these registers for this function call. Then compiler needs to store is original values in the registers X5, X6, and X20 to the temporary storage. And then this temporary storage, temporary memory space is called stack. The stack. So you can find that this last sentence. So we need to say X5, X6, X20 on stack. So stack is the actually temporary memory space. So which means that it's memory. So which means it is in main memory, right? It's not registered. So actually the instructions just handle the data in registers in main memory, right? We already learned. And then the stack is the temporary space in memory. So which means that stack is in the main memory. So which means that we need to store the original values in this X5, X6, and X20 in the stack in the main memory. Okay. Then let's see how this function is translated. Okay. Actually, so this is the function. This function is a LIP example, and then this is the example of the translated with 5 assembly code. So actually, if we see the only this part, like this part, so it's very familiar, right? Actually, I already explained that this statement equal G plus H minus I plus J. So we can find the familiar part in this function, like add X5. So if the X5 is the G plus H, and then we already also had the G is in the X10, and then H is in the X11, and then the I is also in the actually this is the X13. Okay. So actually this part is very familiar. Then we can find the other instructions here, and here. Not here. Here. Okay, here. Okay. So actually, in order to execute the statement in this function, we just require the only this part. This is the main part of the function. But if we see the translated function as the function code, then we can find some conditional part here. So if we see this example, so this is the target of the function. Okay, this is the target. The label in the RISC-V assembly code. So which means that when the main function calls this LIP example function, then main function use the JAL, and then target of the JAL is the LIP example, right? Then the program jumps to the LIP example. So this is the same to the PC of the add I SP minus 12. But also we can find some weird variable so like the SP. So we already learned that in the RISC-V process. So we represent the general purpose registers as the X and the register number. But in this example, we can find the SP. So SP is some alias of the register name, some general purpose register. So actually, SP represents the stack pointer. And then, so this is the SP, and then which also is equivalent to the X1. Okay, so we will learn some other representation of the register file in the later. So which means that so this add I instruction change the stack pointer Okay, so pointer is the address, right? Pointer is the address that points the some memory space. So actually, the stack pointer is pointing the first address of the stack. And then I explained that when this function is called, we need to store the x5, x6, x20 in the temporary space, temporary memory space called stack. So which means that, oh, this is the stack. So first, when stack pointer, it was pointing this address. But in order to store these values, then we need to assign the stack space for storing temporary data. So, and then for this purpose, the stack pointer is changed to this space. Then this function occupies this memory space in a stack and stores this data in the stack memory. Okay, that's why we change the stack pointer like this. So, this we use the store word instruction, which means that the size of data transferred by this store instruction is 4 bytes. So in order to assign the temporary storage for these 3 register values, then we need to occupy 4 multiplied by 3. So this is the 12. So this value is same to is minus 12. Okay. So by adjusting stack pointer by minus 12, when function is called, this function assigns the stack space for storing temporary data x5, x6, x20. So it is because compiler already knows, because compiler will generate these instructions, and then compiler already know that, oh, x5, x6, x20 will be updated by instruction in the function, right? So before executing these instructions at x5 or at x6, at x20, compiler stores the x5, x6, x20 to the temporary space and stack. You understand? So we can know where these values are stored in the stack memory. So this is the original stack, and then the stack is now pointing this memory space. So we know that this is the store word, then this is the address, the target address. The target address is the stack pointer plus 0. So in this memory space, x20 is stored, right? And x6 is stored in the SP plus 4. So this is the x6, and then this is the x5. So in the stack memory, x5, x6, x20 are stored like this. So because these values are stored in the temporary storage, then x5 and x6, x20 can be updated by new instructions, the instructions in the function. And then x20 has the final result. Okay. Then we can find another add instruction here. So if we see that this add instruction, this is the add I, the x10, x20, and 0. So it is actually x20 plus 0 is stored in the x10. And that's it. So why do we require this instruction? So actually, F is calculated by solve instruction. F has the final value, but the F is just moved to the extent. It is because, so actually the RISC-V has certain function procedure rules. So which means that actually these are recommended in the RISC-V ISA manual, and then in the manual, the RISC-V recommend to use extent as the return value. Okay, that's why the X20 is moved to the extent. So in this example, in this slip example, the F is returned to the parent function. So which means X20 is stored in the X10, then parent function will use the value in the X10 to use this return value of the function. Okay, this is the end of the function, right? So this is translated and then this is translated. So F is stored in the return register. And then this is the end of the function. Then what is required? We need to restore the temporarily stored values to the original location. Because it's the end of the function, then we need to return to the parent function, which means that X5, X6, X20, it may be used by the parent function. So when the function call is complete, then we need to restore these values to the original location, right? So where is these values? These values are in the stack space, like X5, X6, X20. So in order to restore these values to the registers, we need to use load instruction, right? Transfer data in the main memory to the register files. Okay. So we already know the address of X20, X6, X5 data. So with the load instructions, we restore the X20, X6, X5. You understand? So these registers are restored. And then stack pointer is also restored. This is the end of the function because this is the end of the function. Because actually these data are restored from the stack memory space. We don't need to use this space. So the stack pointer is restored to the original location. As I explained, these spaces are not required anymore. Okay, so stack pointer is restored, and then return to the main function or parent function. We use the JALR. So if we see that this JALR, we can know that it reads data from X1. Then what is the X1? So actually X1 is the SP. Okay. No. Sorry. Okay. So this is the return address. Oh, sorry. So SP is actually X2. Sorry. So X1 has the return address. So it reads the return address from the X1, and then PC is updated by value of the X1. So what does that mean? So in the lip example is called by a main function or a parent function, then X1 has pointing the very next instruction of this function call. Okay, so the function call is complete, then it returns to the next instruction of the parent function. Okay, using the JALR. So this is how the function call is working. RISC, RISC, RISC-V processor. Okay, I think the SP. So sorry about that. So I will explain about the register use. So SP. So SP is actually X2. Okay. So yeah. So stack SP is the stack pointer, and then if we use the SP, so it represents the X2. And then so this is the some the general purpose register name, like that, from X0 to the X31. So actually we learned that RISC-V has the 32 general purpose registers. But RISC-V assembly code, so we can use the different name for these registers, because RISC-V either manual recommends the purpose of the general purpose register like this. So this is just a recommendation, but when the compiler compiles the high-level language code, then compilers will follow these rules. Okay. So which means that X0 is the 0 register. So we can, which means that instead of X0, we can use the 0 in the assembly code. And then we use X1 as the return address. So this is the return address of the function code. Okay. And then X2 is the stack pointer. So in this example, so SP is used, so which means the SP is the X2 actually. And then X3 and X4 are can be used as the global pointer. So if you see the X5 and X7, sorry, from X5 and X7, these are the temporary registers. Also, we can find the saver here, like the caller and callee. So what does that mean? So what is caller? And then what is callee? So caller is the someone who calls a function. Okay. So I frequently use function call, then it means that the function needs to be called by some parent functions, right? So caller means the something or someone who calls other functions. Who calls other functions, right? It's the who calls. Then what is callee? It's the something or someone who is called. Okay, who is called. So in English, so if we use the so which is the some active person or active things like the employer. But if we use the EE, then it's the someone or something the passively done by active person or active things like the employee, right? So it's same to the caller and callee. The caller is the someone who calls, and then callee is the someone or something who is called. So you can find the saver here. So what does that mean? So it means that so when a function is called, there will be caller or there will be callee. Okay. So which means that when the function is called, caller needs to manage these registers. So which means if X5 and X5, X6, X7 has some important data which will be used later, then caller needs to store this data in the temporary space. Okay. Then how about the X8, X9, and then some like here, it's a saved register or the saved register, and then these registers are managed by wholly. So which means that caller can actually these registers may have some values, and then if the function is called, then wholly. So this function which is called by caller needs to manage these registers. So which means that if these registers are used by a function, then this function needs to store the values in these registers in the temporary space. Okay, so saver represents this meaning. Okay, so actually the RISC-V manual recommends the purpose of the general purpose registers. Okay. Yeah. Yeah. 근데 그 recommendation. So in this example, actually the X5 and X6 are also temporal registers, and then which means that X5 and X, so actually in this recommendation, it should be managed by caller, right? But it's just first recommendation. Okay, so actually, if the X5 and so in this example, we just show that the X5 and X6 are stored by wholly. Okay, so no, this is just a recommendation. Okay, the compiler translates the compiler code, and compiler use these recommendations. Okay, and then also I already explained about the stack space. So stack space are used for storage temporary data in the main memory. So that's why we can find that when the stack spaces are accessible, we use the word store instructions. Also, we use the load instruction. So which means that these are in the main memory. And then in order to use the stack space, so this is the stack pointer, so x2. Okay. So and if a function was if a function requires the most space in the stack space, then the function adjusts the stack pointer until the some memory space required by this function. So that's why in this example, this function needs to store 3 register values, which means this function requires 12 bytes. Okay, so that's why stack pointer is adjusted to the original stack point minus 12 using the add I instruction. So stack pointer is changed to this address, and then we store the temporary values in the stack space. And then if the function call, stack pointer is restored. Also, the values in the stack space are also restored. Okay. Okay. Then let's see the non-if procedure. So non-if procedure. So actually, the previous example shows the if function, if procedures, but there can be non-if procedures, which means that the function is called by parent function, the caller, and then this function may call other functions. Then how can we handle this situation? So this is the example of the non-if procedure. So if we see the difference code, actually this is the recursive function. So which means that inside of this function is the fact function. This function calls its own function, expect. Okay, so inside of this function is called. So how can we handle this situation? Actually, it's the same. So in the previous example, we learned how the deep procedures are handled in a processor. And then, to handle the leaf procedure, the function needs to assign the state space, and then the required data is stored in the state space, and then the function performs some required operations using the instruction, and then it returns to the parent function. So if we see that this function call, so we can find the return data type here, and then we can also find the argument of a function. So we assume that this argument n is stored in the x10. So actually, as you can see, this is the fact function, which represents the actually factorial, like n factorial. Okay. So if we see that this function, and then when this function is executed, and if n is less than 1, it just returns 1. Okay, and then we also assume that the result of this function, the return value, is stored in the x10. And then if the n is equal to 1 or bigger than 1, then the function returns the n multiplied by x n minus 1. Okay. This is the recursive function. So this fact function calls its own function fact, but argument is changing, right? When the function is firstly called by caller, then it uses the argument n. But when the function is called by this function, just argument is changing n minus 1. Okay, so we need to translate this function the RISC-V assembly code. So because this function is the recursive function, the translated RISC-V code is a little bit tricky. Okay, but if we just understand how the function is translated in this previous example, like the function is called, then the state space is occupied, and then some required operations are executed, and then state space is restored and then returned to the parent function. So actually, the same operation is same translation rule is also applied to this recursive function. So actually, if we just see that this condition, the first condition, it's very simple, right? So this is the argument of a function, and then we assume that the argument is stored in x10. So what is required for the first line? We can just compare the x10 with the value 1. And then if this condition is true, like the n is less than 1, then we can just return 1. So which means that the result is in x10, so x10 becomes 1. This is the first line. And then if this first line is not true, okay, then what is required? We need to perform n multiplied by fact n minus 1. So what does that mean? For this return operation, we require n. Okay, this is the argument in x10. And then the argument, the x10, is updated by x10 minus 1, right? And then this becomes the new argument of the fact function. And then this argument is delivered to the fact function. Okay, so what is required? We require, for the return operation, we require n n becomes the n-1, the argument is changed, and then n-1 is delivered to the fact function again. Okay, and then fact function will return some values until this line, right? If the fact function, if the n is equal to 1 or greater than 1, then this fact function will repeatedly perform this line, right? Until n is less than 1. So it will return 1, and then this becomes the result of the fact function. And then, the result of the fact function is multiplied by n again and again. Then result is actually stored in the extent. So what is required? So in order to perform this return operation, we need to know actually n. Okay, and then so which means that we need to store n to the temporary space, which means stack, right? Because n is repeatedly used by this return. Okay, when the function is returned from the result of the fact function, the n will be required, which means that we need to store n in the temporary space. Okay, then what is required? This is the normative function. The function will call other functions. So when the function is called, we use the JAL, right? And then what is required? Actually, when this function fact function is called by a caller, so this JAL stores the return address in x1, and then target of a processor jumps to the target of this JAL. So this is the first line of the function. So first the instruction of the function, right? That's the problem. This function will call its own function, but it can also call other functions, right? So which means that this function will also use the JAL and then target of the function. So it's the first line of the function. And then in fact is repeatedly called again and again. So JAL x1 is stored. It executed. What's the problem? Why do we store return address in x1? It is because we need to know the return position when the function is called. But the problem is that if the function calls other function, the x1 is updated by new position again and again. You understand? Which means that the old values are erased, it's overwritten. You understand? If JAL is executed again and again and again and again, then this x1 is overwritten by new values. And if it was overwritten, then we cannot restore. How can you solve this? Store x1 the temporary space. What is the temporary space? It's stack. So which means when a function calls other functions, okay? Like in this example, the fact function call fact function again, then return address x1 is also stored in stack. Okay, that's the difference. So actually, in this example, in the stack memory, we only store these register values, not the return address. But the function also calls other function. If this function is the non-mixed function, then we need to also store the return address in the stack. Okay. So this is the translated RISC-V code. And then as I already mentioned, actually this code is a little bit tricky to understand. But try to understand this code. So actually, if you, I also include the questions regarding this code in the homework number 2. Okay. So I hope everyone can understand how this function works in a RISC-V processor. Okay, so let's see this code. So you can find that this is the fact, the label of the function. Okay, so it's the first line of the function. When this fact function is called, and then like the this non-mixed example, like the mixed example, stack space is assigned. So stack pointer is adjusted, and then we just store some data to the stack. But if we see this code, so we can find that x1 is stored in the stack, and then x10 is the argument, right? x10 is the n. x10 has the n. But we can find that x1, this is the return address. x1 is the return address. Return address is also stored in stack. Why? Because this is the non-mixed function, non-mixed procedure. So compiler knows that, oh, this function will call also other functions. So which means that the return address needs to be kept. So return address need to be saved. So that's why return address is also stored in stack. Okay. So this is the stack. So as you can see, x10 is stored in the stack, and then x1 is the return address is stored in this space of the stack. And if we see this function, then we need to need to implement the conditional branch, because by this if statement, then the condition by the condition of this if statement, then the operation is if operations are default. Okay, so in this example, we just performs the n-1, and then n-1 is compared with the x0 is 0, right? x0 has already 0 value, and then we just perform the if and if check the n with the 1. So and because the n-1 is n is compared with the 1, so which means that it's the same to the n-1 is compared with the 0, right? So we just check the condition of the n, and then if the condition of the n, if the n is larger than 1 or equal to 1, then put L1. L1 is here. Okay. Which condition? This condition, right? Right? So, and then if we jump to this condition, this operation, then what is required? So as I mentioned, the n-1 need to be delivered to the same fact function, which means that we need to compute the n-1, and then the argument is in x1, x10, so which means that this n-1 needs to be stored in the x10, and then and this return function return is executed, then we also require the n. So also as I explained, the n is need to be stored. That's why in this example, n is already stored in the stack. So in this case, n is already stored in the stack, then we can just propose the n equal n minus 1. So which means that x10 now has the n minus 1. Okay. And this is the argument of fact function. Okay. And then so which means the fact is called. Not called fact, you can just use the JAL, right? So n becomes the n minus 1, and this argument is stored in the x10, and then we can call function again because argument is 10. Okay, so JAL x1 fact. So this jump instruction is executed, and it jumps to this point, then function also execute the same instructions, right? Do you understand? So this line is executed with a minute of just the argument of the function as the n is n minus 1. So we just propose the n equal n minus 1, and then we jump to the first line of the function, the function call, right? And the stack pointer, stack space is updated. So which means the stack pointer is updated again. So what is required? So x1 is the return address, and then x10 is also stored in the stack. So stack point becomes this point. Okay. So actually the n was stored in the x10 here, but n minus 1 was stored in the stack. Okay. Then what is the this x1? What is the this x1? What is the value of x1? So it is actually this is the question in homework number 2. Okay. What is this value? So you can just know the definition of the JAL. What is the definition of JAL? X1 is X1 stored the next PC, right? Right? What is the next PC? The next PC is the PC of add I, right? Because when the JAL is executed, so this is the piece, the current piece, and then the next PC is the PC plus 4, so which is equivalent to the PC of program count of add I. Okay, so when this JAL is executed, X1 has the PC of add I. Are you following me? So this X1. So and then it jumps the fact function back here. So in this stack memory, PC add I is one. PC of add I is one is stored in the stack point, stack space. Okay. Are you following me? Okay. So stack is updated, and then the required values are stored. Now let us assume that the BGE is false. This BGE is false, which means that it's 1. Okay. the VG is false, so which means that this condition. So when this condition is false, so this is the conditional branch, and then if the condition of the branch is false, next instruction, add instruction is executed. So what is the add instruction? So extend becomes the 1. 1 it's same to the return 1 because we will use extend as the return register. Okay. So we update the extend as the 1, and that's it. That's the end of the function. We just update the return register with the return value. Okay, that's it. And like this, we just update the return register. This is the end of the function, and then another required operation is the restoring stack. Okay. So we need to restore stack pointer. Okay. The stack pointer is restored, and then we jump to the caller. Okay. So this is the return. So when the return is executed, then we return to the return address, which is stored in the X1. Then what is X1? So when this JALR is executed, so what is the last JAL? What is the last JAL? The last JAL is this one, right? Because this JAL is executed and we return to this one, and then this is executed. We check the BGE, it was false. Then it encounters return JALR. So actually X1 has the PC of add I. Follow me? Because when the JAL is executed, then X1 stores the PC of the add I. It is also stored in the stack space, but X1 already has the PC of the add I. So which means when this JALR is executed, this instruction will be executed in the next clock. Okay? Because this is the X1 has the PC of the add I. So these instructions are executed. So what is this add I? So this add I, so X10 is moved to the X6. Okay, so this is the result of the fact. Okay, the result of the fact function. And then, as you can see, the data stored in the stack space is restored. So actually, in this example, the stack pointer is updated to this point already, like with this instruction. So when this load word is executed, then X10 is update. X10 has the value of previous X10, which is stored in the stack space. You understand? Because of this add I operation, the stack pointer is changed to this one. Then if we just calculate the address of this load word, then this is the address of this one. So for the stack pointer, the address of the stack pointer And then this is the 0 SP, so which is the X10. And X1 is updated by this one. So what is the recovered? So N is recovered. Also, X1, this is the old return address of this function call. Okay, the old return address is also restored. And then, stack pointer is updated to the original point. Okay, and then it just performs the move. So what is this move? So N is restored to X10, and then the result of fact. The result of fact is in the X6. So what does that mean? This is the N multiplied by result of fact function. This is also stored in the X10 and return. So in this case, the X1 is updated by previous return address, right? Because this return address is restored from stack. So which means, the return point of this X1, this program jumped to the return point of this old return address. What is this? It was just stored by this instance. So in this case, I assume that the N is just 1, right? Right. So N is just 1. So which means that the fact is just for once. So which means that when this JALR is executed and the old return pointer is restored, and this old return pointer will be the main function, the parent function of the fact. So let us assume that this is the main function, and the inside of the main function we just for the fact here, then we need return to the very next term, the fact function code. Okay. So this is the example of the non-repeat procedure. Actually, just remember that when a function calls the other function, then we need to remember that the X1, the return address is overwritten. Okay, so in order to avoid this case, this return address is also stored with the stack. And then when the function is returned from the other function, then the return address is restored from stack again and again. Okay, so which means we can also jump to the return point when the function call completes. That's the example of the non-repeat procedure. So actually, so this is a little tricky because so in this example we use the recursive function, so which means the function calls its own function, but the baseline policy is the same, right? So as I explained, by this condition we can use the BGE, but only difference is that so we need to store the return address, okay, in the stack. So this is the example of the non-repeat procedure, and I hope you can understand how this instruction, how this assembly code works. Okay. So this is the kind of memory layer. Actually, for this memory thing. So this is the end of the example of the function code, and then I will explain about the memory layer. So when our high-level language code is translated, then binary code is generated. But the memory space is assigned to the compiled binary code. So it means that when the binary code is executed, so it means in the Windows we can click some icon and we can execute some application, right? Or in a CLI like the Unix or Linux operating system, you can just type the command of the binary file and then we can execute this binary file by input the file name. Then if the file is executable, then we can execute this binary file. Then if the compiled binary file is executed, the memory space is assigned to this binary file. Okay. Okay. If the binary file, the executable file includes some text data, which is the instruction, which are instructions. So instructions are also the data. So these instructions are stored in the binary file like the text data. Okay. And then when the some binary files are executed, then these files also include the static data. So static data means that if the data space is statically managed, statically assigned in the memory space. Okay, it is not dynamically managed, like some constant, like so we can also define the static variables. So actually, if you use the C, you can find some static variables. Okay. So these constant values or static variables are stored in the static data space. And then this space is located over the text space. So the text space is just the instructions, compile the instruction, and the static data is located over the text space. And so the programs are running, we can dynamically use some memory space. So if you are familiar with the C, then you can find some syntax is it's a function, right? Actually function. So like the memory allocation function is called the malloc. So if this malloc is executed, then the memory space is dynamically assigned in the main memory. Like if we use the malloc A and then size of A, right? So A is some pointer. This means the pointer. So which means that this space for A is dynamically allocated in the memory space. So this dynamic data is also managed on over the static data. So it increases to this direction. It starts from the final space of the static data, and then it increases to this direction. And then how about the stack? Stack is the temporary space. So stack starts from the final, the last memory space assigned to a program. Then stack increase to the low downward, so like the low direction. Okay. So if you see the stack address, then you can find that initially the stack address. This is just an example. So what you can find the stack pointer is pointing the last address of the assigned memory space. And then stack increases to the low direction. So it's in the previous example, you can find the add I stack pointer minus 12 like this. So stack is just decreasing because stack space increases to the low direction. So if this stack pointer meets the dynamic data, this situation is called the stack overflow. So the kind of some exceptions. So you can find some many programming advices in the Stack Overflow site. Because Stack Overflow means the stack means the point of the dynamic data. Okay. But recently the large memory spaces are assigned to the program. So again, usually the programmers do not consider the Stack Overflow. Sometimes Stack Overflow happens if we write some incorrect code. Okay, that's how the memory spaces are assigned to instructions and then state data, dynamic data, and stack. Okay. Okay. So and then just remember the stack starts from the last space of the assigned memory space, and then stack increase so goes down and the stack is increased. Okay, so in this class I explain about how the list functions are handled and how the non-list functions are handled. Actually, this is very important part of the chapter 2. Actually, it's a little bit tricky because right? And actually, branch instructions or jump instructions are somewhat more difficult than the other normal instructions, but it's some important part of chapter 2. So I hope everyone can understand how these functions or procedure codes are handled in the process. Okay. Okay, I will stop here. And any questions? Also, as I mentioned, I also made the problems regarding this part. So please solve the problems by yourself. Okay. Okay, thanks for attention, and then see you in the next class.